So let's start off with the module 5 named Opamp Circuit. So in this module, we are studying about digital to analog converters. In that we have two types, weighted resistor and R to R ladder type. And in analog to digital converter, we have successive approximation type to study, and followed by small signal half wave rectifiers and active filters, including first and second order low pass as well as high pass Butterworth filters. And along with that, we have band pass and band reject filters to study. And second part of the module 5 is related to 555 timers and its application. In that, we have monostable and astable multivibrators to study. So for this module, we are supposed to refer the textbook 2, that is Opamps and Linear Integrated Circuits by Ramakant A. Gayakwad. So let's start off. First, we have digital to analog converters, and in that we have two types, that is binary weighted resistors and R to R resistors. Not only these two, there are many other types, but in your syllabus you are supposed to study about binary weighted resistors and R to R type DAC. So what is DAC? So DAC is digital to analog converter, which will take the output of the digital system and it will convert it to equivalent analog voltage or current. So what will be the output of the digital system? It will be obviously the binary output. So basically, binary input is given to DAC and will get equivalent analog voltage or current. So first we have digital to analog converter with binary weighted resistors. So here, this is the configuration of DAC with binary weighted resistors. So these are the binary weighted resistors, namely R by 2, R by 4 and R by 8. Since there are 4 binary weighted resistors, this is considered as a 4-bit binary converter, and these are the switches, 4 switches, B0, B1, B2 and B3, which will connect these resistors to the power supply volt of 5 volts, and this is connected to the inverting configuration of the op-amp. As you can see here, non-inverting terminal is grounded, and here this feedback path has a feedback resistance of 1 kilo ohm. So this is simple. First we'll consider switch B0 is closed. So when it is closed, this resistor is connected to the power supply of plus 5 volts. In the first case, we'll consider B0 is closed, and in the second case, we'll consider B1 is closed. And for our understanding, we'll consider both switches B0 and B1 closed, and we'll understand the working of the DAC with the binary weighted resistors. So first case is wherein we are considering switch B0 is closed. So when this is closed, the current through the resistor R is equal to V by I. V is 5 volts and V by R, R will be 10 kilo ohm. So the resulting current through the resistor R will be equal to 0.5 milliohm, and since in ideal case this input current to the op-amp is equal to 0, the same 0.5 milliampere will flow through the feedback resistor. Okay, so that will give me the output voltage as equal to 0.5 milli into 1 kilo ohm, that is equal to minus 5 volts, minus because this is inverting op-amp, and so the output voltage is equal to minus 5 volt when switch B0 is closed. Now we'll consider the second case wherein switch B1 is closed and B0 is opened. Now B1 alone is closed. So the resulting current through the resistor R by 2 now will be equal to 1 milliampere. Now the same current will flow through the feedback resistor. So here also I'll get 1 milliampere since the input current to the ideal op amp is equal to 0. So the output voltage will be equal to minus 1 volt in this case. So it is doubled when I compare it with case 1 wherein only B0 is closed. So you can see there is increase in the output voltage, but in the negative direction. It is minus 1 volt. Now consider both switches are closed, B0 as well as B1. So the resulting output voltage will be equal to minus 1.5 volts, because see here 0.5 volt as well as 0.5 milliampere as well as 1 milliampere together 1.5 milliampere will flow through the feedback resistor RF, that is equal to 1 kilo ohm, and I'll get the output voltage as equal to minus 1.5. So you can see as in when the switches B0 and B1 are closed, the output voltage is increasing in the negative direction. So here we have a staircase wave in the negative direction indicating the output voltages with respect to the decimal equivalent of the binary input. So this is about the binary weighted resistor DAC, and the output voltage is given by minus RF into B0 by R plus B1 by R by 2 plus B2 by R by 4 plus B3 by R by 8. Here if B0, B1, B2 and B3 are closed, meaning the values of B0 is equal to 5, B1 if it is not connected to the power supply, B0 is equal to 0. If B1 is connected to, meaning switch is closed, B1 switch is closed and is connected to plus 5 volts, the value of B1 is 5 volts. If it is not connected, it is 0 volts. So these switches B0, B1, B2 and B3 can either be 0 or 5 volts. So this is about binary weighted DAC converter. And next we have DAC converter with R and 2R resistors. Here also same, the binary inputs are simulated by the switches B0 to B3, and the output voltage is proportional to these binary inputs, and these switches can either be, or the binary inputs can either be plus 5 or 0 volts. So this is the configuration of the DAC converter with R to R resistors. Why we call R to R resistors is there are only two resistors here. One is R and the other is 2R. R is R resistor is equal to 10 kilo ohm and 2R is twice of that, so it is 20 kilo ohm. So they call it as ladder network because it forms a ladder type. You can see the 2R resistors are connected in parallel, so this part it looks like a ladder. So this configuration is also called ladder type or 2R DAC. So this is the configuration of the DAC converter with R and 2R resistors. So now we will, in this case, we will assume that switch B3 is connected to plus 5 volts over here, okay, whereas all the other switches are grounded, okay, as shown here. Now, so only this part of the circuitry is directly connected to the op amp now. So till now this part of the circuitry we are now going to use Thevenin's theorem. So by using Thevenin's theorem, I will get the Thevenin's equivalent resistance that is represented by RTH, and I will get it as equal to so much. I'll explain you how we'll get that. So here you can see 2R is in parallel with 2R. So 2R is in parallel with 2R, and this is in series with this resistor R. So here you can see 2R is in parallel with 2R and is in series connection with a resistance R. So this much we understood, and next we have this part of the circuit we have reduced. Now this much is in parallel with this resistor 2R, and it is connected in series with the resistor R. So you can see that in this part of the equation, this much is in parallel with resistor 2R, and this is in series with resistor R, that is this resistor. Now this reduced part of this circuit is in parallel with this 2R resistor, which is in series with the resistor R. So till here, till this much part of the left part of the circuitry, we are going to Thevenize. So here it is in parallel with 2R, and R resistor is in series. If any one of you have doubts regarding this equation, you can ask me. If you have any doubts, I'll clear it. So upon solving, you will get the Thevenin's equivalent resistance as equal to 20 kilo ohm, and by the concept of virtual ground, you can see that the non-inverting terminal of the op-amp, that is V1, is connected to ground. So by the concept of virtual ground, V2 is also at ground potential. Okay, so you should understand, apply apply virtual concept here to this op-amp, and you should also know, apply the ideal op-amp condition, that is input current to the op-amp is 0, and after Thevenizing you will get the reduced circuit as shown in the figure B, that is till this part of the circuitry from the left side we have Thevenized, and the Thevenized resistance, equivalent resistance, is given by RTH, and is equal to 2R, and this 2R resistor is written here, and it is connected to plus 5 volts. So here we have written plus 5 volts, and here the configuration remains the same. And so what after applying virtual concept, V2 is also at ground potential. So the current through, so here the current through at the Thevenin's equivalent resistor is equal to 0, because it is connected to ground, and here the potential at V2 is also 0 because of the virtual ground concept. So current through this is also equal to 0, but the current through this 2R resistor that is connected to this switch and to the power supply is equal to 5 by 20 kilo ohm, that is equal to 0.25 milliampere. And now this 0.25 milliampere will flow through this feedback resistor RF. So V0 will be equal to 0.25 milliampere into 20 kilo ohm, that is equal to minus 5 volts. Understood? So now the output voltage equation can be written as minus RF into B3 by 2R plus B2 by 4R plus B1 by 8R plus B0 by 16R. Because see here, B3 is connected to 2R, and here B2 it is 4R, and here B1 by 8R. It keeps on multiplying by the factor 2. So here also B0 can be either 5 volts or 0 volts. So this is about R to R DAC converter. And next we have today about analog to digital converter. That is, it converts the analog signal into digital signal. Here we have a successive approximation A to D converter. So here we have 8-bit successive approximation resistor, and this is 8-bit latch, and this is 8-bit DAC. And here we have a comparator. The output of this DAC is given to the inverting terminal of the comparator, and to the non-inverting terminal we are giving analog input V in. So it compares the output of DAC and analog input, and based upon the output of the comparator, the SAR will set and reset these bits. Okay, and based upon that, the next operation is decided, and all the data will be stored in this 8-bit latch. The operation of this is very simple. So first, to start off with the conversion cycle, this SAR will set this signal start to high, and it will first set the most significant bit, that is MSB, to 1. Okay, and this DAC will give me the equivalent analog voltage VA, and this is compared with the input voltage. Okay, now if the comparator output is low, which means the output of the digital to analog converter is greater than Vin. If Vin is lesser than the output voltage VA by the DAC, the comparator output will be low. If Vin is greater than VA, the comparator output will be high. Now, if the comparator output is low, the SAR will clear its MSB, that is Q7. If it is high, the comparator output is high, the SAR will keep the MSB Q7 to 1 itself. Understood? If it is high, it will remain the same as 1. If it is low, it will clear. So next, in the next clock cycle, Q6 bit is set. So set meaning Q6 is high. So this DAC will consider this binary input B0 to B7 and will produce an equivalent analog voltage VA. Now this is compared with the analog input voltage Vin, where if Vin is lesser than this VA, the comparator output will be low and it will clear this bit Q6. If it is high, this Q6 will remain in high state, and in each and every state, this 8-bit latch will be storing the data and will be giving the digital output data. So this is the operation of the A to D converter. Once the conversion is complete, this is set to high. Okay, so the advantage of this successive approximation type is its high speed and excellent resolution. So this, since it is an 8-bit data that we are operating with, it requires only 8 clock pulses to complete the conversion from analog to digital. So this is about the analog to digital converter, and in the next session we'll continue with the further topics.